Well, thank you for the introduction. Could you hear me well?
Yeah.
Okay, so you can see the slides. Right?
Yes.
Okay, sounds good. So yeah, so project I'm going to talk about today is using nanoparticle tracking method to understand the nanomodels transporting the porous medium. So nanomodels, also called nanoswimmers, are active particle, is a type of particle able to take energy from the environment and converting it to directional flow. A classic example would be like catalytic genus particle. For example, for this kind of particles, it usually half side was coated with metal like platinum. And this metal able to make the reaction of hydrogen peroxide into water and oxygen, which will create a concentration gradient and cause like diffusion of phoresis. And this will cause a self-propulsion effect. Therefore, when we look at the particle trajectories in the unconfined liquid, compared to the traditional and conventional Brownian particle, and I show you here, which is usually random walk because it only have diffusions. When we increase the concentration of the hydrogen peroxide, which is a chemical field, we can see that the active particle became more directional, and the displacement of the trajectory at certain time scale is much significantly larger than the Brownian particle. So we can see that compared to the Brownian particle, it only have a diffusion mode. Active particle have diffusion and self-propulsion mode. And because of this more complex transport mechanism make it have huge potentials in the a lot of applications. For example, like biomedical application, environmental application, all kinds of applications. But that is in the unconfined liquid. For all the applications, it's usually in the confined environments. So understand how they transport in the confined environments is very important. A lot of groups did some very good experiments. For example, in here, they observe the nanomodels able to move around the rectangular geometry. And in this paper, they found that the nanomodels able to circle around the spheres. But all these are qualitative observation, and they observe this phenomenon. And also, if you look at this kind of confinement, we can think confinement have all levels of confinement, from the less confined situation to the more confined situation. All this is more simple confinement. But in the real world applications, it could have much more complex confinement, like in the spheres and the pores. And how we understand their transport in this kind of super confined scenarios, and how we quantitatively study this, which is the key for us to push the nanomodels for the further applications for like industrial applications. Therefore, the objective of my project is using some method to quantitatively study this process, especially how nanomodels compare to Brownian particle, how fast they transport in the porous medium. Well, first I'd like to give you a very general introduction about porous medium. Porous medium is a kind of structure which you see everywhere. For example, the separation membranes and also the soil system is also a very good porous medium. When we think about the porous medium, it usually have like two kind of structures. The first is this kind of pores, the larger pores. And second is the pore connection, connected the pores, which we also call this holes. So, but when we think about the nanomodels or Brownian particle transporting this structure, it usually can be considered like two processes. And we consider this as a rate-determined process, which is how the particles transport from this kind of one confined space to another confined space. And this escape process usually consists two decoupled process. First, you need to search for the opening on the cavity. Second, you need to translocate through the openings. So during this project, I just want to quantify how fast, given no models confining this kind of sphere, how fast take it to translocate from one cavity to another. Well, first I want to introduce you for this kind of escape process could search limited and barrier limited, because search limited is how fast it search for the opening, and barrier limited is more like object finds the opening, whether it's able to escape from this very narrow channels. If there is like potential energy, it maybe make it very difficult to translocate. And because of that, for this escape process, it can be divided into two modes. One is like this kind of search limited escape process. So for this search limited process, the particles escape immediately upon encountering an opening hole. While for the barrier limited escape process, maybe there are this kind of energy barrier like electrostatic barrier and entropic barrier at the whole exit. So which means that this barrier will decrease the probability of escape. So in order to quantitatively study this, we want to find a very good like model system. Here I'm using a highly ordered porous medium, which is silicon inverse opal film. So I want to use this one because it's a very quantitative study model. If we look at this SEM image, we can see that it has very uniform cavities. And for each cavity, it will have 12 holes connecting the cavities. And also, we are able to systematically control the fabrication process to make systematic hole size and cavity size. Therefore, we are able to study like how the geometric parameters influence the transport process. And secondly, in order to see the particle inside of this material, we need a very advanced tracking system. Here I'm using a three-dimensional single particle tracking system. So for particle tracking is a very conventional experiment to study like corridor system, but usually it's like 2D tracking. In here, because this geometry is very complex, and if we want to accurately extract how this translocation process, we really need 3D tracking. So how I do this? I insert a special module called the face mask module, which converts the conventional like point spread function into this engineered point spread function. Then you can see that usually light source on the microscope, it will show like this circular signals. And in here, I engineer it into two lobes. And these two lobes, we can find the XY position by the center place. And then we can find the Z position by the angles of these two lobes. Therefore, if we're looking at the videos, we can see that the particle confinement inside of this material, it usually have like two kind of movement. One is first confined in this kind of sphere, and the second is translocate through this sphere. And if we look at these videos, we can see it also have two types of movement. One is like fluctuating around certain space, that is confined, and then suddenly it will move its angles or positions, and that is it hop to the adjacent cavity. Therefore, with this experiment set up, we are very easily to quantify the particle transport inside of this porous medium system. Now, let's look at some experiment result. And here I show you two results. On the left is conventional passive particle, only have diffusion. And on the right is the Nanoswimmers, which is active particle. In addition to diffusion, it also has self-propulsion effect. These are our experiment data. They are particles trajectory, and the different color represent different time scale. So which means that, for example, if we look at the trajectory map on the left, so the particles first confined in this kind of cavity on the on here, which is the dark red color, and then it will went through this trajectory direction and move to this white sphere. However, for these Nanoswimmers, we can see that this movement is so different. If you can look at carefully, you can see that first, for this passive particle, the trajectory is more confined inside of these spheres. And while for the nanomodels, it's more likely to all move around the boundaries. So you can see here it's all move around the boundaries. So from here, we can see a very interesting phenomenon. First is the Nanoswimmers exhibited different like search models. So this one, as we described, is search around the boundaries, which we saw a lot from previous studies. But second thing, very interesting is for this one, the trajectory on the left, in 3 minutes, it only been like 3 cavities. While for the Nanoswimmers, in just 1 minute, it already went 4 different cavities. So which means that the Nanoswimmers search much faster than the traditional Brownian motion particles. So the next question is, we want to quantify how fast it is. To do that, I did the escape time analysis. Escape time analysis is that for each kind of trajectory map we discussed in previous slide, that from here we can extract how much time the particles stay in one cavity before it escape. And then we can get this kind of time series analysis information, which is how particles XY position as a function of time. We can see that from this kind of analysis, we are able to find like the dwell time before escape. For example, in this passive case, we can see that the escape time could be over 100 seconds, while for the Nanoswimmers, the escape time is only like 1 second or 15 seconds. It's significantly smaller. And after that, if we get thousands of these trajectories, we can plot the Sojourn time distribution. And this is the probability as a function of time. And from this, we can get like the mean Sojourn time, which means what's the mean time for particle confined in this structure, take it to escape to the nearby cavity. And then we can see that for the passive particle, which only have Brownian motion, the mean Sojourn time is about 70 seconds. While for the Nanoswimmers, it's only like 3 seconds. It's significantly different. And here, we found that the difference is about like 25 faster for the Nanoswimmers in this kind of cavity escape process. Right now, I want you guys to think about that. Okay, so we see that Nanoswimmers move faster and escape the cavity much faster than Brownian particle. But you think, of course, sure, because it has the self-propulsion effect. But we want to understand how much the self-propulsion effect makes this to move faster. And is this the only reason to make it faster? And because 25 difference is so significant, therefore the first thing we did is analyze the mean square displacement. And from this mean square displacement, we are able to get the particles like diffusion coefficient at the short time. We can see that the diffusion coefficient for the narrow swimmers and the passive particle, the narrow swimmer is only like 2 times mobility in the unconfined liquid. So this study is first in the unconfined liquid. So, so what we found is that, okay, yes, the narrow swimmer should move faster than the Brownian particle, and in the unconfined liquid, it's only 2 times faster. But if we put in this confined environment, we see a significant transport enhancement. So then why is that? To understand this, first, we did a bunch of experiments. And in this experiment, we changed the different hole size and also measure how this mean sojourn time as a function of this hole size. And this solid data point is the experiment data, which we have just passive Brownian particle result, and also we have the narrow swimmers result. And we also did the Monte Carlo simulation, and this simulation is simulate how using the experiment data input to see how fast a particle will transport inside of this structure. And we can see that we are able to like simulate the result of the narrow swimmers very well. So we can see this is on-field points overlap with the experiment data very well. While the passive particle, yes, we see some discrepancy. Therefore, in here, we can see that there could be like 2 escape modes. In the first one, the passive particles, why is different? Because in our simulations, we wouldn't be include the energy barrier as a whole exister. We only consider this like a search limited process. Therefore, this difference between the Brownian particle and the experiment data and the simulation result is because this kind of energy barrier. So we can see that the first part difference may be because the self-propulsion force overcomes the energy barrier and converts the escape process from this kind of barrier limited to search limited. And the second thing is we want to see that the difference between the passive particle from here to the narrow swimmers, they are so dramatically different. We want to see what's the second part difference, why it move faster. Well, to answer this question, I want to make a particular example, like if we just look at this one hole size is about 500 nanometers, what's the difference between the passive particle and the narrow swimmers? We can see that the total difference is about 25 times. So the first part, the self-propulsion force overcomes the energy barrier is count about 5 times. And the next 5 times, what that come from? Well, to understand this, we first thinking is, okay, let's compare the diffusion coefficient inside of this confinement. Therefore, we calculate the MSD again, but this time is in the porous medium. What we can see that here is the passive particle result and narrow swimmer result. Very interestingly, when the diffusion coefficient difference in the unconfined liquid for these two kind of particle is only like 2 times different. While when we put into this confinement, the difference become like three times. So because of this, we think that the narrow swimmers search even faster in this kind of confinement. Why is that? Because the confinement could amplify the concentration gradient around the sphere, and therefore it will create a much significant self-propulsion effect. And the second reason is we think what we observe frequently is that the narrow swimmers tend to move around the boundaries of the sphere. So we thinking that this kind of different search mode maybe create a significant difference. So we found that if we plot their like probability of the particle's position as a function of the distance to the center of the cavity, we can see that the dashed line is the wall. That we can see this is the narrow swimmers. The narrow swimmers is more likely to get very close to the wall, while the passive particle is more likely to stay away from the wall because of electrostatic repulsion or other microscopic interactions. Therefore, because of that, we found that the narrow swimmers may be search much more efficiently for the existing holes by moving around the cavity spheres instead of exploring the entire cavity. Well, if we combine these two conclusions together, that one is maybe the narrow swimmers search faster, and the second thing is maybe a search smarter, able to move around the boundaries, which is a much more advanced search algorithm. We did another simulations which we decouple these two processes. For one case is only considered is a diffusion coefficient different, and the second case is we only consider as the same diffusion coefficient. What's the difference if it just search inside of the cavity or search around the boundaries? And here's the result. If we look at the 500 nanometer hole size again, we can see that right now we found the difference between the passive particle and this simulation result is like 5 times difference, which is exactly what we were looking for previously. Therefore, let's look at this result again. So previously, here I showing you this result, which is the mean Sojourn time as a function of hole size for both passive particles and narrow swimmers. And we found that there is significant difference for the escape time for the passive particle and narrow swimmer. Passive particle move much slower, so the mean Sojourn time is significantly larger. And the difference between these two because of 3 reasons. The first difference is the barrier limited elimination, because when there is passive particles there is the energy barrier at the whole exit, which prevents the particle move out. So when we have the self-propulsion effect, it provides additional kinetic energy to overcome that energy barrier. So this accounts the first part of acceleration. And the second part is what we discussed previously, the enhanced mobility and surface-mediated search, which is particles able to search faster and search smarter in this confinement. Search faster is because in confinement, it exaggerates the concentration gradient difference, so makes the self-propulsion effect more significant. While for the search smarter, because the narrow swimmers able to search around the boundaries, which make it have a much advanced search algorithm, so that able to find the exit much faster. So take home message from this presentation is that we found that a significant difference for the transporting side of the porous medium between the Nanoswimmers and the passive Brownian particle. And when people think about this difference, they usually consider this because of self-propulsion. And we will simplistically calculate by speed. But in our analysis, we found that this self-propulsion could actually induce additional nuanced effects, like elimination of energy barrier, search faster and smarter. And this effect impacts is actually dramatically amplified in the confined environment, and which lead to the enhanced transport, which we observed. Lastly, I would like to thank Dr. Schwartz and other group members at the University of Colorado Boulder and the funding support from Department of Energy. And if you have any questions, you can ask now. And for other people, if you have questions afterwards, feel free to contact me, and this is my email address. And with that, I'm happy to take any questions.
Okay, thank you. Thank you for your last talk. Let's see if we have questions or comments from the audience. Please feel free to unmute yourself if you have questions. So any question?
Oh, there is a question in the chat. Oh, the question here is how I achieve the tracking and identification of particle 3D motion trajectory in page 8. Okay, so let's go back to page 8. Oh, okay. So maybe I think for the tracking is in this part, page 6. So how I achieve like 3D tracking is, first of all, for conventional like fluorescent microscope, is able to identify the particles very well by fluorescent signal or other like refract index difference. And at here, what I did different is insert this kind of face mask module. And this kind of module able to like convert the regular point spread function into this kind of like double helix point spread function. And from here, we can find its safe position by this angle of these two lobes. And this is, for now, is already a very well-developed method. And if you're looking at just Google like 3D tracking and double helix point spread function, and you will find a lot of papers discuss how to use this method and very comprehensively. And they even have equipment you can directly purchase. This is commercially available. And also for the tracking software, I think they also have the open source tracking software. And for page 8, what you ask is how I like identify the 3D motion is, first of all, for this part, as I said, it already have some open source tracking software you can use. From here, you can get particles trajectory. And this particle trajectory here are plotted, but actually it's just X, Y, Z position as a function of time. Therefore, we can plot this one. And for this one, how I identify all this kind of movement, what I did is like a fluctuation analysis. What this is that you can see that for particle confined in the cavity and escape will have significant difference. For example, if we just look at this blue lines, what we can see is that it suddenly will shift from one stage to another stage. So as long as we can observe this kind of shift using some algorithm, it's very easy to identify the movement inside of this porous medium. Yeah. Any other questions?
Hi, Dr. Wu. Can you hear me?
Yes.
Very nice talk, Dr. Wu. May I ask a question? Like, could you repeat again? What do you mean the search smarter for the swimmers?
Oh, sure. So search smarter is, I think, in here. Search smarter is if you read some papers about the narrow models, what usually people observe is that the narrow swimmers just like to stay around the boundary, right? To move on the boundaries of some. So, and this phenomenon is make it easier to find the opening in the porous medium compared to that the passive particle, which is just stay inside of the porous medium and don't move around the boundary. So that difference make it search much faster, and I call this search smarter. Yeah, you can see that they have different search mode, right?
Okay, yeah, I got you. Yeah, but I kind of don't feel it's exactly the smarter as traditionally we understand. Like, for example, like you can use some machine learning method to find the holes or something. That's what I understand smarter, but that's a different way. Yeah. Okay.
So yeah,
Okay.
Go ahead.
No, I'm finished. I finished. Sorry.
Okay. Thank you.
Thank you.